Hello and welcome to this AQA Statistics video, the second in the series looking at discrete random variables, this time looking at the Poisson distribution. So in this video we're going to be looking at events occurring randomly in time or space, and this occurs quite frequently in real life. And we're going to be looking at some examples where we're interested in counting the number of events that occur within a set time or space interval. And we have a little example here where we could count the number of births that occur in a hospital during a day. That's our time interval. And what might we want to use this for? Well, we could perhaps work out the average number of births per day at the hospital, and then perhaps use that information to make predictions about staffing in the future. And we'll look at a few more examples of this on the next slide. So following on, the number of cases of a disease that occur in a particular town, we have our space interval, the town, and the number of cases should occur at random. Looking at mutations in a particular space, a particular area of a chromosome, how often those occur, they should be random, and possibly counting the number of particles emitted by a radioactive source in a given time interval, say perhaps 10 seconds. So the discrete probability distribution that's relevant to the situation of counting events that occur randomly in a given time or space interval is the Poisson distribution, first proposed by Simeon Poisson and named after him. The probability function you can see here is the function for a discrete random variable x. Remember, capital X describes the event we're interested in, and small x describes the specific events that are possible. And do note that with the Poisson distribution we have discrete outcomes 0, 1, 2, 3, but notice there is no end to that. We have an infinite number of possible outcomes, and that's different to the binomial distribution situation. We have a parameter involved here, so we're looking at lambda that occurs twice here. Lambda can take any positive value, and lambda is the Poisson distribution parameter. So you've already met n and p as the parameters for the binomial distribution, and mu and sigma for the normal distribution. Lambda is the parameter involved with the Poisson distribution. And the notation we use is x follows a Poisson distribution, and inside the brackets we state what the value of lambda is. So for example, if our random variable follows a Poisson distribution where lambda is 4.5, we would write it in this way. So that formula is in your formula book, and we'll look at how that can be used later on in this series. And notice that the probability function also involves the constant e, and you should have already met this constant in pure maths, and it's also a very important and useful number in statistics, as well as in calculus and complex numbers, etc. in pure maths. So if we now just look at the shape of the Poisson distribution, this example here just illustrates how the Poisson distribution is characterized by this positive skew. However, the shape of the Poisson distribution does vary dependent on the value of lambda, the parameter. And if we just look at probability calculator on GeoGebra and plot for one or two values of lambda, first of all notice that actually in GeoGebra they don't identify it as lambda, they put mu there, and you'll discover why later on. But this is a plot for the discrete Poisson distribution where lambda is 1.5, and again you can definitely see that evidence of positive skew. when we increase our value of lambda to 4.5, the skew isn't quite so obvious, but you can still see a bit of a tail here. And once we reach the point where lambda is now 15, you can see that you almost have a symmetrical bell-shaped curve, as you perhaps have come across with the normal distribution, although of course here our distribution is discrete. So if we consider a random variable x, such as the ones we've looked at before, representing the number of occurrences in a time or space interval, x can be modelled by a Poisson distribution if those events occur at random or can be assumed to do so. If the events occur independently of each other, so one random event occurring has no influence on the likelihood of another random event occurring. And also the average number of events in a given time or space interval, and as I mentioned when we looked at GeoGebra, that average actually is the Poisson parameter lambda. That must be constant, and that rate lambda is proportional to the interval. So if we knew lambda, say the average was 4.5 for a 10-minute interval, then lambda can be assumed to be 9 within a 20-minute interval. And also, finally, events must be able to be counted and identified individually. So we say events must occur singly. So looking at some examples here and considering those conditions, and you may find in an exam question you may be asked to criticize a particular example and say whether or not you believe the Poisson distribution is a good model or not. So thinking about those conditions, insurance claims made by motorists per month. And I think one thing that would perhaps stick out there is that perhaps in the winter time, where weather is more likely to be unfavourable, there may be a lot more claims made, so the average per month might not be constant over a whole year. Secondly, the number of cars passing in a 10-minute period on a road, it very much depends on the type of road. If you've got a large road where you've got a fairly constant flow of cars, that would be fine. But if you've got roadworks holding cars back, then the events are not going to occur at random or even independently of each other. And it may be, if there are lots of cars there, the events can't be considered to be occurring singly either. So that may be a good model, but there may be reasons why not. And finally, the number of errors in typing on a particular page of a document. Again, that might not have a constant average per page, dependent on how difficult a particular typing was on one page. It may be there was perhaps a lot of mathematical typing on one page, and other pages were more straightforward. And that concludes this video.